Hi, I recently got a couple of small 1.54-inch ink displays with a resolution of 152 to 152 pixels. They have three colors, and in this video, I'll design a PCB using KiCad and order the boards and program them to create a functional device. I'll also design and 3D print a custom case to give it a polished look. This is the display that I've got. I got this display on a recent 40% off deal, so I bought several. They're about $6 each now, so it's worth checking their website for deals like that. I also picked up one of their adapter boards as well, so I'll use that for prototyping. These displays are marketed as three colors, but in reality they only use two types of pixels. When no pixels are activated, the display treats that state as a third color, which in this case is simply white. In addition to white, the display has black and red pixels that you can use. This type of multicolor ink displays are generally slow to refresh, but they are very energy efficient because they consume only power when the display content changes. Another reason why I love ink displays is that they look like regular printed paper. For this project, I plan to use ESP32-S3 chip. I recently designed a development board with it and was impressed by how easy it is to work with. I'll use that previous design as a template and build on top of it. If you are interested in that part, you can watch the related video by clicking the card or the link in the description below. My current plan is to place a connector for the ePaper display in the center of the board and decide a suitable position for the buttons as well, and also ePaper driving circuitry, maybe something like this. I also want to keep as many pins available as possible so the board can be used for development purposes such as connecting additional sensors, etc. However, for now, I have another application in mind. My wife has been studying French and I want to turn this into a word of the day device that she can keep on her desk to display the words she has already learned. Since the ESP32-S3 supports native USB, I plan to make the device appear as a flash drive when connected to a PC, allowing her to easily add or remove the words. I also want to make it possible for her to manage the word list wirelessly using her phone. Before doing all that, let's first test the displays using the adapter board. Using these types of boards are very useful before designing your own PCB, as they let you verify that the pins you plan to use are compatible with the MCU that you intend to use. By the way, don't mind the huge capacitor here. I was experimenting with something weird and got too lazy to remove it. The nice thing about good display is that they usually provide example code to get started. It's not always comprehensive, but it's sufficient to jumpstart your project. I downloaded their code and uploaded it, only changing the pin definitions to match my setup. I connected my ESP32-S3 board and the pins I plan to use in the PCB design to test if everything works. Let's take a blank display and test whether it works as I intend to use it. As expected, this display is very slow. It takes 10 to 15 seconds for a full update. I'll try to speed it up later by modifying the driver. Now that I know it works, I can start designing the PCB. I'll start by downloading the Ducky board ESP32-S3 from GitHub. I designed this board to be as inexpensive as possible to manufacture, so I'll continue building on top of it. Good Display also provides schematics for the adapter board, so I'll copy everything from here and put it into the KiCad project. And here is my KiCad schematic. This part is the same as the previous design that I've got, so I didn't really do much over here. In here, I copied everything from the Good Display's adapter board schematic with a few small but important changes. These differences may be minor, but they can significantly impact the cost, especially for the small production batches. These small differences depend on the PCB manufacturer you choose. JLC PCB is sponsoring this video, so big thanks to them. I'll focus on their services and share the tips to make your design as cost-effective as possible, including the assembly, which they handle very efficiently every day, even for the small batches. The first tip is to use the components from JLC PCB's basic parts list. They don't charge engineering fees for these parts, so using as many components as possible from the list helps to keep costs low. Fortunately, most of the components like capacitors and resistors are available in this list. The easiest way to find parts you need is by using the parametric search. Just make sure to double check details like rated voltages to avoid damaging any components. And sometimes you may not find a specific component, like in this case, a 0.47 ohm resistors isn't available in the basic parts list. These situations are easy to solve. For example, you can just use two 1 ohm resistors in parallel to get 0.5 ohm. It is roughly equal to 0.47 ohm, which is close enough since this isn't a critical resistor. And also we have 1 ohm resistors as a basic part in JLC PCB, so it is going to be cheaper. There are also cases where a part is only available in the extended part list. So, for example, this Scotty diode itself is inexpensive, but the added engineering fee makes it cost more overall. In such situations, it's better to look for an alternative from the basics part list to keep the costs low. For example, this Scotty diode isn't just on the basic part list, but also it has better specifications and also cheaper too. And that's why I use that one instead. One thing to watch out for is the component specifications. For example, there is a 10 microhenry inductor in the schematics, and while there are two available in the basic parts list, it's only rated for 15 milliampere. This is the max rated one, and this one is even lower than that. However, the good display schematic specifies an inductor rated for 1 ampere. I'm not sure if the display actually draws that much current, even momentarily, but I didn't want to take any chances here. So I went with the cheapest inductor that has 1 ampere rating, even though it's from the extended part lists. It's also a good idea to define the footprints and the part numbers by double-clicking components. This will be helpful later when designing the PCB and during the assembly. By the way, if you don't have a manufacturer part number field, you can add it by clicking this plus button here. There are a few other minor differences, such as MOSFET selection and some resistor values, but overall my schematic is essentially the same as the good display adapter board schematic, so we can switch to PCB editor by clicking this button and start designing our PCB. Alright, here is the previous PCB that I designed. Since I am building on my earlier project, I don't need to spend time on redoing most of the existing work, especially around the microcontroller and near the antenna area. Let's import the components that we added to the schematic by clicking this button. And here we click Update the PCB and press close. If all the footprints were defined correctly in the schematics, they'll appear on the PCB layout like this way. I want to keep the top section of the previous PCB and place the new components in the lower half of the board, essentially making the PCB a little bit more denser. First, I delete the copper zones to make the layout clearer and easier to work on. Let's move the components that we plan to reposition out of the way to create some room for us. I usually place the bigger parts to the location that I want to put and then put the smaller parts next. That way it is easier to route and place the components. After placing the larger components, I group related parts close to where they belong. For example, all these components here are part of the ePaper driver circuitry, so I'll position them near to this connector here. Essentially what I try to do is putting these all parts which are under the same box closer to each other. Also lithium-ion charging circuitry, that's also another group here. There are a few good reasons for doing this. First, it makes routing much easier, which becomes increasingly important as your design grows and more complex. Another reason is to reduce the electromagnetic interference and maintain signal integrity. By grouping components truthfully from the start, you usually won't have to deal with these issues later, which can be a real headache if the parts placed carelessly. Alright, I placed all the components on the PCB and routed most of the connections except ground and USB signals. Before going into details, there's an important point to mention about the routing. It's the board setup. You need to configure the board settings to match your manufacturer's specifications. In this case, JLC PCB, these settings can be found under the File Board Setup menu. You should align your PCB design with your manufacturer's capabilities, in this case JLC PCB, and you can find all the relevant specifications on their website, including the tolerances, under the capabilities link, and those are mostly relevant to tolerances, trace widths, and other design limitations. But if you don't want to set this up yourself, you can simply download my project and delete everything and start your own design. My project already has all the settings configured to match the JLC PCB's capabilities. And in my design, all the signal lines are 0.2 millimeters, but also there are power lines like this 5-volt rail here, and those are, I put it like 0.6 millimeters. It is more than enough thickness, so you won't have any issues there. One of the coolest features of the ESP32-S3 is the native USB support. You can use it for programming or make the chip act as a USB device. You need to follow specific design requirements. The most important is routing differential signals so they match each other. KiCad supports this automatically, so you don't have to calculate anything manually. Just go here and press and hold the left mouse button and select Route Differential Pair. After that, KiCad will route the two USB lines simultaneously. Make sure that they stay away from the other signal traces and you should be good. I routed my traces like this, and usually I try to keep traces horizontal on one side and vertical on the other, but I couldn't fully achieve that here. Still, it should work fine like this. Let's define our key part areas. I am going to click on this button, Draw Rule Areas, and just draw a rectangle. What I don't want here is especially the fill out zones. I'm gonna click on that and just draw something like this. And we can, of course, refine it later on, depending on your needs, but this should be enough for now. And next, let's draw the ground zones. I click on this button, Draw Filled Zones, and select ground here, both on the front and the back panel, and just draw something which covers entire PCB. As a final step before sending it for manufacturing, let's run the design rules checker to see if we missed anything. And don't forget to check in refill all zones before performing DRC and click DRC button here. It will check all the rules that we defined. I solved all issues which is catched by design rules checker, and we can see how it is going to look like after the manufacturing. So I didn't have the 3D models for the buttons and such, but more or less the design will be looking like this after we send it for a manufacturing. After that, I use the Fabrication Toolkit plugin to export the design for manufacturing, and then we are ready to order the PCB. Go to Tools and External Plugins and click Fabrication Toolkit and click Generate. It will create everything which is necessary to manufacture your design. Since we completed our design, let's order it. Go to JLC PCB and click Order Now link over here, and you will see this page. And click Add Gerber file and select the Gerber files that fabrication tool created for us and wait for them to upload. The only thing that I'm going to change here is the color, and apart from that, I'm not going to touch anything over here. For a design like this, the default settings are enough. And if you want to just order the PCB and do the soldering yourself, you will pay around like $2 for 5 pieces. You can also ask them to create a stencil for you and ship it together, but I don't want that because I'm going to order a PCB assembly for this board. And I'm gonna click this button and we'll select assemble on the top side because there is no component on the bottom here to make it a little bit cheaper. You can just go with the standard settings here because we are not doing anything special. Then I will click next. This is the next page that you will see, and I'm going to click next and add the BOM file. The BOM file is the BOM CSV and CPL file is the positions file, and after that just click Proceed BOM and CPL. There's an error popped up saying that 3.3 volt and antenna designators don't exist in the CPL file. Since they are not really a component, we can just ignore this error and click Continue. It's important to verify all the components are correct here. Let's move down a little bit. There are unmatched components because we don't really have any pin header in the JLC PCB part list, but that's okay because we don't want them to solder it on the board. And I'm going to click Next again, and I say don't place them. And on the next page, we can check if the components are placed correctly and the orientations are correct. For example, the ESP32-S3 did not place correctly. I can understand that from the dot over here. I'm going to rotate that, clicking this button. The rest of the parts seems to be placed correctly. I think I can just move forward. And this is the final pricing. For 5 boards, it costs like $115. It's equal to $23 for each board. And if you order more than 5 boards, the total price will increase, but price of a single board will drop significantly. For example, a simple and fast calculation, it will reduce to around like $10 for each board if you order like 20. Our PCBs arrived after a few days, and this is the most exciting part for me, seeing all the work come to life as a physical object. Let's grab one of the screens and test if it works right away. I soldered a lithium-ion battery and gave it a quick charge via USB. I also programmed the board with the same sample code from the good display. Let me install the screen first. I used double-sided tape to make the setup a bit more rigid for the further development. Without a case, the ePaper screen can move back and forth, which puts stress on the flex cable and can eventually damage the connection. I was considering designing and 3D printing a case and showing my firmware development progress, but the video has already gotten quite long and I don't want to turn it into a 30-minute video. The ESP32-S3 has some great upgrades compared to the previous ESP32s, allowing for even more interesting projects. With features like native USB support and a low power core, there is a lot of potential. So let me know in the comments if you'd like to see my progress on that as well. I think it would easily take at least a full video to cover, and it's worth making a separate one if you also agree. But for now, if you enjoyed this video, don't forget to give it a thumbs up, and I'll see you next time.